Welcome to this video on quantum mechanics grammar, focusing on Bra-Ket notation. This mathematical language is essential for describing the subatomic world. Dirac notation, unified wave mechanics, and matrix mechanics. It allows us to calculate quantum outcomes without excessive complexity. It is the fundamental alphabet used by every quantum physicist. Our learning roadmap includes understanding the core concepts, the ket, the bra, and the inner product. We will then mathematically derive projection and identity operators. We begin with part 01, the Ket vector, which represents the column of possibilities in a quantum system. The ket is denoted by a vertical bar, the symbol psi, and a right-angled bracket. Theoretically, it is a state vector in Hilbert space, holding all information about a quantum system. Mathematically, in a discrete basis, the ket acts like a column vector. Each entry, or alpha, represents the probability amplitude of the system being in a specific state. The direction of the Ket vector defines the particle's state. Furthermore, adding two kets creates a new ket, representing a valid superposition state. Next is part 02, the Bra vector, often called the row of the dual space. The bra is represented by a left-angled bracket, psi, and a vertical bar. It is the dual vector of the ket, residing in the dual space. To turn a ket into a bra, we perform a dagger operation. This involves turning the column vector into a row vector and taking the complex conjugate of its elements. The bra is the adjoint of the ket. In matrix form, the bra is a row vector with elements that are the complex conjugates of the ket elements. This ensures that when we combine them, we yield real physical results. We now move to part 03, the bracket, which is the inner product calculation. Combining a bra on the left and a ket on the right forms a bracket, or the inner product. Mathematically, it is a dot product, resulting in a single complex number. The braket is calculated by multiplying each corresponding pair of components, using the complex conjugate of the bra components, and summing the results. This summation represents the total overlap between the two states. The braket measures the similarity between two states. Its absolute square gives the probability of finding a particle in state phi if it started in state psi. This is the Born rule in Dirac notation. The probability P equals the magnitude squared of the bracket. This is the crucial link between vector math and physical measurements. Part 04 covers operators, which are the verbs in the grammar of quantum mechanics. An operator A acts on a ket psi to produce a new ket psi prime. This is analogous to a matrix multiplying a column vector, transforming the quantum state. While a Braket is a number, a ket bra is a matrix. This is called an outer product. This matrix represents an operation that can be performed on other quantum states. The simplest outer product is the projection operator P. Formed by a ket n and a bra n, it acts as a filter, extracting the component of a state that aligns with the basis vector n. Applying the projector P to state psi results in the projection of psi onto the n-axis. The probability amplitude, the bracket of n and psi, scales the basis vector n. Part 05 explores the concept of completeness, also known as the resolution of identity. The resolution of identity states that summing every possible projection operator for a complete set of states yields the identity operator I. This confirms that all possibilities for the system are covered. A key trick in Dirac notation is inserting the identity operator I in front of a state psi. This mathematical maneuver prepares the state for expansion without changing its physics. By replacing the identity with the sum of projectors, we expand psi as a sum of basis vectors n, weighted by the amplitude bracket n psi. This confirms that every state is a superposition. Part 06 discusses orthogonality, the independence of possibilities in a quantum system. Basis states must be orthonormal, meaning their overlap is 1 if they are identical, and 0 otherwise. This is represented by the Kronecker delta and ensures states are physically distinct. Normalization requires that the inner product of a state with itself equals 1. This ensures that the total probability of finding the particle anywhere in the universe is 100%. Part 07, the sandwich, addresses calculating expectation values. The quantum sandwich finds the expectation value of an observable A by placing the operator A between the bra and the ket of state psi. This number is the statistical average of measurements. To extract a specific element of an operator matrix, we sandwich the operator between two different basis states, M and N. This connects Dirac notation directly to matrix mechanics. Part 08 provides a summary, covering the master checklist of concepts. Here is a glossary of the symbols used throughout this video. Dirac notation matters because of its efficiency in cutting through complex math, its clarity in defining components, and its universality across all quantum systems. As Paul Dirac stated, mathematics is the tool specially suited for dealing with abstract concepts of any kind. In a continuous basis, such as position states, the discrete sum transforms into an integral over all possible positions x. The identity concept remains the same. The traditional wave function, psi of x, is merely the inner product between the position state x and the quantum state psi. Dirac notation shows it is a representation, not the state itself. By defining Kets as vectors and Bras as duals, we've established a consistent algebra that preserves probability, allows basis expansion, and calculates physical averages efficiently.